Okay, let's start. Today in this lecture we'll briefly look at how we might go about designing analog circuits in practice. And before we start with it, I want to bring your attention to a couple of parameters that we use for transistor. The first is, of course, this metric GM by ID. This is something I introduced in the first lecture. So as we saw that class, this essentially is a metric of power efficiency. It says what is the maximum GM you can extract from a transistor when you bias it at a particular drain current, or the other way is to get a particular GM, what should be the bias current I should have. So in a way you can say that this captures the power efficiency of the transistor. Okay. And from your memory, tell me, do you think this ratio is higher in strong inversion or in weak inversion? In weak inversion we saw, and again if you want to recollect, in strong inversion this ratio was 2 by the overdrive voltage, 2 by VGS minus VTH. In weak inversion it was 1 by M times the thermal voltage. So let's say now I try to plot this metric. I think this was again a problem I gave you in the practice set. Let's do that. So let's say I try to plot this ratio GM by ID versus VGS. Okay. Now if let us say there was no weak inversion, right, that is if only strong inversion existed, how would this characteristic look like? Inversely proportional. And what will happen around VTH? It will blow to infinity. So if only strong inversion existed around VTH, I mean for larger, we will draw it more reasonably. So let's say this is roughly the threshold voltage. So for larger VGS it follows 1 by X relation, no worries. But if it was only strong inversion, it would have blown up to infinity. But now you know for smaller VGS it saturates to this value, okay, something like this. And but nevertheless the fact still holds that it's in weak inversion you get the maximum GM by ID ratio. So in a way this also tells you the region in which the transistor is biased, whether it is in strong inversion or weak inversion. Okay. So now the second metric is of course the intrinsic gain, which is GM R naught, right. So okay, yeah, and if the transistor is in saturation, what is the value of R naught in terms of the bias current? 1 by lambda ID. So this I write it as GM by ID times 1 by lambda, right. So once again you see this metric also gives you information about the intrinsic gain of the transistor. Okay, cool. So now let's say I have an NMOS transistor biased with some VGS and some VDS. Let us say it carries a current I1. Let us say it has a width of W. Let us say I take an identical transistor now, connected to the same VGS and VDS. This also has the same width W. What would be the current here? I1. Fine, same VGS, same VDS, same transistor. And I'm sure you guys know, or if you don't know, this entire thing can be thought of as one composite transistor whose width is what? 2 times W. Okay. So connected to the same VGS and VDS. So now you see that the current here is 2 times I1. Fine. So from this discussion, tell me how is the drain current related to the width of the transistor? Directly proportional. Okay. So now let us say on top of this VGS, let me draw it neatly, I add a small change delta V. What would be the change in the drain current here? GM delta V. Similarly, what would be the change in the drain current in this transistor? Same. So what would be the total current here? 2 times GM delta V. So again you can think of it like this. Here I have 2 GM delta V. So now based on this observation, tell me if I have the same VGS and VDS and if I double the width of a transistor, what happens to the GM? Doubles. So under this condition, GM and W, how are they related? Directly proportional. Okay. So now you see current is proportional to W, GM is proportional to the width. So what can you say about this ratio GM by ID? Independent of? Okay. So this I will say it's independent of width. By the same logic, what can you say about the intrinsic gain GM or not? Independent of it, because it's essentially GM by ID by a constant lambda. So this also can be argued to be independent of width. I mean, by extension, you can also say that this ratio ID by W, GM by W, they are also independent of width. Fine. Okay, so now let me list down the parameters that we have noted down that are independent of width. So first was the ratio GM by ID. Next we saw the intrinsic gain GM or not, or I will say GM by GDS. And then we saw even the ratio ID by W or GM by W. They are also independent of it. And by the way, this ratio ID by W is called the current density. It essentially says the current per unit width in the transistor. It's some kind of a density measure. Okay, so now I want to introduce another parameter which is called the transit frequency. So it is defined as follows. Let us say I take the same NMOS transistor and excite the gate with a small signal current I in and short the output. Okay. Now ideally what would be the gate voltage? If I pump in a current into the gate, what do you expect the drain voltage to be? It's an ideal current source. If I pump in an ideal current source into the gate, what do you expect the gate voltage to be in an ideal scenario? Yeah, why? Yeah, it's open circuit, but if I pump in current into an open circuit, what should be the voltage? What is the resistance of an open circuit? If I push in a finite current into an open circuit, what should be the voltage? It should technically blow up, but in practice, what do you think will happen? I mean, in practice, this is not ideally open circuit. You also have capacitances. So you will have a capacitance between gate and source as well as gate and drain. So I will club everything and call this to be an effective capacitance CGG from the gate to ground. Okay. So then tell me what is VG in Laplace domain? VG of S in terms of I in. I in by? Is this fine? The current times the impedance of the capacitance, that's what. So which means what is the short circuit current now in Laplace domain? GM times the gate voltage. So it's essentially GM by SCGG times I in of S. So I'll basically call this to be. Okay. So this can be thought of as current gain. That is, I pump in a current and I see what the output current here is. So here at what complex frequency S do you think this gain becomes unity? for what value of S this portion becomes unity? Gm by, so that is what is defined as the transit frequency, wherein the current gain's magnitude becomes 1. Again, this was relevant when people were using bipolar junction transistors, where you actually had a current gain, but still with MOSFET the definition kind of still stuck. So in a way, this defines the speed to which you can or you can say it's a proxy for the speed of a transistor, right? Because remember, we have delay in our circuits because you have capacitances and you need finite time to charge or discharge the capacitance. So here it captures the capacitance also, and GM in a way says what can be the current that transistor can deliver. If the current is larger, do you think it will be slower or faster? If I can push in a larger current, do you think the speed will be faster or slower? Faster, right? So in a way, this captures the speed. Yeah, but it doesn't mean that, let us say if I find that the FT of a transistor is 100 gigahertz, it doesn't mean that I can go and operate the transistor at that frequency, but it serves as a comparison. So if I have two transistors, one has a 10 gigahertz of FT and the other has 100 gigahertz of FT, it is clear that the one with the higher FT can be used at higher frequencies. Just as a comparison of speed, we can use this. Okay, so now we already saw for fixed VGS and VDS, the GM was proportional to W, and even CGG, how do you think it's related to W? It's essentially, capacitance depends on the area. So if you scale the area, this also scales. So then what can you say about this ratio? That is also independent of it. So I'll include this ratio also in this list. Cool. So now let us say you are planning to design a circuit, and in your circuit for a particular transistor, let us say you find that the GM has to be something, and you also somehow fix the bias current to be something. Now ideally, how would you go about deciding the ratio W by L? How will you find it? If I know these two fellows, how will you find the width typically? I mean, don't say something that you kind of, in an ideal setting, how would you do? I mean, I know the GM, I know the current, how will I find the width? I mean, let's say I gave you right now, or in your previous course it was given to you. Huh? I mean, let's say, without finding overdrive, can I find the ratio W by L from GM and ID? What will you do? GM is under root 2 ID mu C OX. So from this, typically, since you know the current, I know GM. If essentially you know this fellow, you can find W by L. Then you can assume a particular length. Then that will give you the width. Okay. So if things were all nice, this would have worked. But there are a couple of things that works against. First, finding this value is not tricky. And second of all, this relation is based on the square law model for a transistor, where we define ID to be this to the overdrive square. Again, it turns out this equation is grossly approximate if you already don't know. So in practice, we have much more complicated compact model which will have hundreds of parameters. So it is not practical to take into account all of this and try to design it. But still we use this equation because it gives you some design insights. See, it might not be true that ID is proportional to V overdrive power 2. It might be something like this. But the fact still stands that if I increase overdrive voltage, current increases, GM increases. And similarly, we just saw that ID is actually proportional to W. This is exact, there is no confusion. So this kind of basic design insights you still get. So that is why you still learn this equation. Okay, so now that we established we can't use this equation exactly for designing in practice. So let's see what we do. So what we do is the following. So as a designer, what parameters of transistors you are interested in? I mean, if you are designing an amplifier, let us say, what parameters you will be interested in? GM. What else? Yeah, WL. And I mean, let's start with small signal. What are the small signal parameters you will be interested in? Yeah, the gain, that's basically GM or not, or I will say GDS. You also want to know about the gate capacitance because that determines the speed. And let's say you also want to know about the bias conditions. So let us say the drain current ID, the VDS, VGS, and as you guys mentioned, you also need to know about these two. If you are talking about capacitance, why are you interested in drain to source capacitance? Combined it's CGG. I mean, drain to source capacitance is typically small. Okay. And out capacitance. What is out capacitance? That is not a design const. I mean, that is not a transistor parameter, right? That is some spec given to you. Okay, so now let us say you go and make a huge database or a lookup table which says for each possible values of width, for each possible values of L, for each possible operating point. So this is the operating point. And you note down what are these values. Let's say GM, you note down GM, GDS, CGG, ID. So now we have established a huge database which says for all possible dimensions, for all possible operating point conditions, what would be the parameters I have. So now let us say in your design for a particular transistor, you find that I need to get a particular GM. Then you look into this database, you will find that to get a particular GM, you will have a whole bunch of options. You can use different combinations of widths and lengths, different operating point conditions. Then you can choose one of the options, and that you might choose based on a lot of things. So let us say you want to reduce the power consumption, you may choose an option that has the smallest current, and so on. That's the basic idea. Right? I mean, it's essentially how Zomato and Swiggy is doing. So they have a huge database of all restaurants nearby, all the dishes and corresponding cost. So one day you want to have, let's say, biryani or pizza, you search for a particular dish, it lists out all the possible options, and then you choose one option, you choose one restaurant, maybe based on how fast it's going to come or the ratings or the cost. Same way you do. Just generate a database, look back into this and choose an appropriate option. Right? It's pretty trivial. So now to generate this database, I will have to essentially sweep the width, generate this database for all possible values of width, for all possible values of length, and also have to sweep the operating point. So I'll have to do sweep VGS, VDS, and in practice you also have the bulk terminal for a transistor, if you guys already don't know. So you have a fourth terminal called the substrate or bulk. So that also affects the operating point, so you have to include all this. Okay. So it's like a for loop. You have 5 nested for loops. You sweep all possible values for all of these and then store these guys. That's how ideally you have to generate this lookup table. But let's say let's see if we can do something smarter, right? So based on the discussion we have had so far, can you suggest me some modification I can do here so that I don't have to sweep one of the variables? Huh? Yeah, as you're saying, we just saw some parameters here are independent of width. So instead of storing these parameters which depend on width, if I can store these as a proxy, I know they are independent of width, I don't have to sweep the width. Right? So which means instead of saving GM, what parameter I can save? I can save GM by ID, or I can save GM by W, either is fine. Instead of GDS, what can I save? GM by GDS. Or another thing you can do is you can also take GDS by ID. I mean, that is essentially 1 by R0 times ID. Correct? And as you know, R0 is 1 by lambda ID. So that just becomes 1 by lambda. Or So this also is kind of constant. Instead of CGG, what can you store? The transit frequency GM by CGG, and instead of ID, the current density ID by W. So now we know these parameters, they only depend on 4 metrics now. So I just have to sweep the bulk to source, VDS, VGS and length, that's it. And again, these parameters we are saving, they are not some arbitrary parameters. As we saw, each of these is actually an important metric for a transistor, right? We saw GM by ID, we saw GM by GDS, GM by CGG. Similarly, each of them has some meaning. Okay. So now that reduces your job by this. So now you just have to sweep 4 variables. Right. Now if you want to reduce your job, you can maybe ignore the effect of VBS to start with. That will reduce it even further. Or even to make it one order easier, you can sometimes ignore VDS also. So you can generate lookup table only by sweeping these two. But I have to warn that if you ignore the VDS and VBS, the lookup table will not be exhaustive and correct. So you might incur some error, right? So if you use this lookup table to design, the final result you get will be slightly off from the ideal value. But again, for simplicity, you can maybe ignore these two. So is the basic idea clear? It's pretty trivial. It's essentially creating a huge lookup table like Zomato and then search and get it. The smartness comes in the fact that instead of saving these fellows, you are saving parameters which are independent of it. That reduces the complexity so that you don't have to sweep the width now. Okay. So this approach is typically called the lookup table based approach, or the people who first came up with this, they called it GM by ID based design. Cool. So now if I had to list down the steps you have to follow to generate this lookup table. Now I just have to sweep length and VGS. So it's essentially like this. Again, you have to generate this lookup table for both NMOS and PMOS, right? Because you will be using both transistors. So it's essentially like having a for loop. I'll start by sweeping the length. You start from the, let us say, the minimum possible length, 2 times the minimum length, and so on. Ideally, as many different lengths as possible. So that is the first. What is the second parameter I have to sweep? VGS. So second for loop will be, again, this is just a pseudocode kind of thing I'm writing. You sweep VGS from 0 to whatever maximum value you have. And then what parameters I should store? All the width independent parameters. So I'll just say store GM by ID, say GM by GDS, let's say GM by W, GDS by ID, GM by CGG, ID by W, etc. Right? All kind of width independent parameters you store and then you finish it. That's it. So now sweeping the length is trivial. You take a transistor, have a particular length. Once you finish this thing, you change the length and do it. Now for sweeping VGS, of course you can do this. You can basically do this. You can connect it to, let us say, VDD or something, and then directly sweep the VGS like this. Or you can also do it this way. You can essentially diode connect this and change the current. That will automatically change the VGS. Either of them is fine. But the point to note is, when you are getting these parameters, you should make sure that the transistor is in saturation. because finally that's where you want your transistor to be biased. So you ensure that's happening. So is the idea clear how we are generating the lookup table? Okay, let us say now I have created the lookup table. Now let's take a simple case. Let us say for a particular circuit you find a transistor must have a particular GM. Let us say from some other thing you also found the current ID. Now my goal is to find the width and length, right? Now tell me which parameter I know here. I know which parameter? I know GM by ID. From these two I will know GM by ID, and I need to find the dimension width and length. So which parameter I can look at now? Now I know the current, I need to find the width. So I can basically look at ID by W. So what you can do is you can plot GM by ID as a function of ID by W for different possible lengths. Let us say L1, L2, L3, etc. Okay. So let us say I do that. This is an example. So let us say I am getting some plot like this. Okay, this is GM by ID versus the current density. I have chosen 5 different lengths. So starting from the minimum length to 5 times minimum length. So let us say in your design you find the ratio GM by ID required is some 15. So this is the value you want. Now we can choose any of the length, right? Because you can get the required GM by ID for any possible length. So let us say you choose the minimum length. So this is the white is the minimum length. Now you find that to get this particular GM by ID, you need ID by W of something, right? So I just looked at GM by ID, that gave me what should be the current density. I know the current, so I can find the width. And I have assumed the length, so length is also, you know. Is the idea clear?
For increasing
that is something that you think. That will be an assignment problem. You are asking why is the graph going this way as an increased length. Is that question? Is that the question?
Yes.
Yeah, that you can think, right? I will give it as a practice set. I mean, you can use your basic square law understanding and see and predict how the curve should shift. Whether if you increase the length, it should come this way or go this way. So this is how you do. Okay. And I mean, you yeah, in your simulator you can actually save the operating points. So you can just do this. You can print the operating point this way. Results print DC operating point. And you know your simulator will throw out so many operating point details, like you can see I don't know where, the drain current ID, you can see the GM over ID, etc. And you can also ask it to store all these operating point, like you can go to outputs, save and operating point parameters and save all this. Again, you will get so many resources online to do this, or I'll ask the TS to upload a document. This is a trivial thing. So now let's take a simple toy example and then see how you can do this. And of course, the more complicated circuits I'll ask you to design. I'll only design a simple common source here. I'll take a simple common source as an example. Okay. So let us say the spec that is given to you is only the DC gain. That should be roughly about 10. That's the only spec given to you. So what is the DC gain here in the circuit? What is the DC gain here from VI to V out? GM times? I mean, can you be exact? Yeah, RD parallel R naught, right? This should be roughly about 10. That's the only spec given to you. And from this, you are supposed to design the transistors, GM, current, width, length, overdrive voltage, everything. So this is how a typical design problem in practice will be. you will be just given less constraints, but you will have to solve for more design variables. It won't be like I have 5 equations, 5 unknowns, I solve it magically, get one magical point, and that's your like design. Okay. So in practice, design problems are heavily under constraint. So you'll have more variables to design for than the constraints given to you. So which means you have to make reasonable approximations, assumptions, and move on. Okay. You can't expect like a proper 10 equations, 10 unknowns case. Okay. So let's say this is the spec. Right. So now between RD and R naught, you can have 3 cases. I can have a very large RD, or I can have a very large R naught, or I can have both of them to be of the same order. Now, I mean, from your circuit understanding, tell me, if I have a large value of RD, what can be a problem here? Huh? Yeah, we know that the bias voltage here is VDD minus ID times RD. If I have a larger RD, this voltage will start to drop. That might push the transistor out of saturation. So a reasonable thing to assume is R naught is much larger than RD, which means RD is small. Fine. So which means how does this approximate as GMRD? That's it. So this is what I want. Okay. This is the first approximation, or sorry, not approximation, assumption I am making. Okay. So if GMRD has to be 10, how much should be GMR naught? It should be much greater than GMRD, right? Because I have assumed R naught to be much greater than RD. So GMR naught is much greater than 10. So typical number, let's say I choose it to be about 100, roughly 10 times greater, to be safe. So which means I know GM by GDS here. Okay. Now from this I have to find the transconductance ID, width and length. So let us say, I mean, if you want to find the current ID, what parameter you might look at now? I know GM by GDS, that needs to be 100. If I want to find the current ID, which parameter I can look at, do you think? GM? GM by ID is fine. So let us say I do the following. I look at, okay, let me do this. So I know GM by GDS. So I can plot this versus GM by ID for different values of length. Okay. So I do that, I get something like this. Okay. So this is GM by GDS versus GM by ID, and for different lengths. So here, can you tell me this is the smaller length or this is the smaller length? As you increase length, the gain should increase or gain should decrease? If I increase the length, R naught of the transistor increases or reduces? Huh? It should increase. Okay. So which means this is the way in which the length is increasing. Fine. So here I know that my GM by GDS must be 100. So it's pretty clear I cannot use these two. I cannot use the minimum length or 2 times minimum length. Right. So I can choose any length greater than this. So let us say we stick to this 3 times minimum length. So this tells you for this particular value of 100, the current density must be somewhere here, and I think that's about 10.8 or something. Okay. Sorry. So let me mark it here. So this gives me what is GM by ID, that's about 10.8. Similarly, to find the width, what parameter I can look at? I can look at ID by W, GM by W, anything. So let's say I look ID by W and I find that, I'll directly give you, this was about 5.75 I think. If I had to write the units also, this is volts inverse, this is ampere per meter. Okay, so now Still we have to find out these things. I have to find GM, I have to find RD, I have to find ID, I have to find width. The only thing I have assumed is I have assumed the length to be 3 times the minimum length. Okay. I still have to find 4, and I have only 1 equation, 2 equations and 3 equations. I have 4 unknowns and 3 equations. So how would you go about solving this? Huh? I have 3 constraints, right? GMRD, 1 constraint. I just found that for a particular GM or not, I also know GM by ID and ID by W, but I have 4 unknowns. So how would you go about solving such equations?
We know GM times W.
Yeah, that's what I'm saying. This is 1 equation. This is another constraint we got from this. You have 3 equations and 4 unknowns. How many possible solutions you can have? Technically infinitely large. So to choose a solution, what would you do? You have to assume something. I can assume any parameter here. So what let us say I assume RD. I assume RD to be 10K. Again, random. Okay. You could have assumed any other parameter also. If RD is 10K, how much should be GM? 1 millisiemens. Correct. So now I know GM. From this I can find the drain current. The drain current is GM by 10.8. So I think that came out about 96 microamps or something. I'll directly give the number. So this I am finding based on these two. Okay. From the value of GM I found and the ratio GM by ID, I find the drain current ID. Okay. Now I need to find the width. That's the last thing pending. What will I do? I already know ID by W. I just found out ID. So yeah, so I use these two information. That gives ID to be about 17 microns. Okay.
Like even question from previous example,
Mm-hmm.
where we knew we plotted GMID versus ID by W.
Correct.
Like in the simulation, when we use this, won't we already know the width of the transistor?
Yeah, but you are not saving the width finally. You are just saving the ratio ID by W. Right?
Okay.
The idea is to generate the width independent parameters.
Okay.
That's all.
So in that example, we are not essentially trying to find anything. We are just seeing the variation.
Yeah.
Yeah.
See, when you are first getting these parameters, wherever it goes, as he's pointing out, you assume some width, right? Yeah. But that doesn't mean anything. You are essentially normalizing everything so that the width goes off, right? And one thing I forgot to mention is when you are doing this experiment, don't use a very large width or a very small width, because in practice the transistor models can be widely different for a very small width or a very large width. So you use it about 1 micrometer or so for generating these plots. Okay. So this way design is over, but one thing is, once you do this design, you have to make sure that the transistor is nicely in saturation. Okay, that is something to always check. So after designing for small signal, you verify the operating point is fine. Verify if it is in saturation and in strong inversion. Okay. So here you can quickly do. Now I know what is GM by ID, ID by W. I can quickly look at the corresponding VGS. Okay. And in this case, I think the VGS turned out to be about 0.6 volts or something. Okay. So VGS is roughly 0.6 volts. And this you get basically from any of the plots. Let us say you plot ID by W versus VGS, or GM by ID versus VGS. From there, the idea to notice, for a given ID by W, or I would say this way, if you choose a particular length, the moment you fix Gm by Id, all the other parameters are fixed because they are not very independent. So what I mean is this: the moment you fix a length, once you fix Gm by Id, all these guys are fixed. Okay. So yeah, here you find VGS. I have to find VDS, and what is setting the VDS here? So the VDD minus IDRD. VDD in this process was 1.8 volt. So that's about 1.8 minus the current was 96 microamps times 10k. So I mean, this you can work out. This will be roughly about this is what 100 micro into 10k, 0.1. So yeah, this is about 0.8 volts. So now you see that this is the drain voltage is 0.8 volts. So it is safely in saturation, no need to worry. So this is something that you checked, but you also have to make sure that this is in strong inversion and not in weak inversion, because we saw in the first class with respect to speed, we want our transistors to be in strong inversion, because in weak inversion we have a very large width, currents are small, so the speed is typically limited. So how do you find whether it is in strong or weak inversion? Yeah, but that is true, but a better thing to look at is this, right? In the beginning, what he told is exactly that, but yeah, so you can look at this plot, Gm by Id versus VGS. So in here I will know that if I am reaching near the saturated region, I am in weak inversion. If I am nicely in this varying region, I am in strong inversion. Okay, that is something you can do. So if I do that, yeah, this is the Gm by Id versus VGS for the length I have chosen. I have chosen 3 times minimum length, that is the length, and our Gm by Id was how much? Gm by Id was 10.8. So 10 is here, 10.8 is somewhere here. So it is nicely in the slope region. So we can guarantee that it is in strong inversion. Whereas if you had found your Gm by Id to be lying somewhere here, then it is more and more towards weak inversion. Okay. So this is something to always keep in mind. Make sure that after designing for small signal parameters, verify the operating point and ensure that it is in strong inversion and in saturation. Okay, so now I did a quick simulation for this. So the same circuit, and typically the transistor is biased with a constant current, not with a voltage. So let us say I have the required drain current as a current source. How can I generate the corresponding VGS? Sorry? So you can take an identical transistor here, and let's say do this. This will generate the required VGS that will make sure the current here is 96 microamps. Fine. So now I have the bias voltage VB, I have a small signal voltage Vi. How will I connect the two? Use a large resistor and a large capacitor, something you should have seen in the first course. So but this is a simulation, so I just put the source like this. I mean, typically the small signal sources are with respect to ground. It's a simulation, so I mean, who cares? I just did this. Okay. And when I did this, these are the results I get. This is the operating point. I don't know if it's clear. So as you see, I wanted a Gm by Id of 10.8 roughly. I get the same, and our Gm was how much? Gm was 1 millisiemens. So here you can see Gm is about 1.04 roughly, right? And the drain current is about 97 microamps. Again, there are minor variations because in generating the lookup table, I discarded the effect of VDS. If I had also included VDS while sweeping and generated that massive lookup table, this would have been spot on. Okay. Because of that, there is minor variation, but this is much better than what you would have gotten if you stuck to the square law model and tried to find new COX blah blah blah. If you are just stuck to square law and try to design it, you will find that the results you get will be way off. So you have to go back and change your design. So you will be doing a lot of back and forth. Okay. Yeah, and I also plotted the gain here. So this is the gain versus frequency. For very low frequencies, the gain is constant. You wanted a gain of 10. How much is this in log scale? Huh? Okay, I mean 20 log of 10, right? That's what you do. How much is this? 20 dB. And that's what you get. This is in dB. It's about 19.8 dB, right? So this is how you kind of go about designing transistors in practice. Okay. Any confusions, questions? I mean, don't worry about the exact way in which I design. That is just one way. Right? A design can be, I mean, in practice, there can be thousands of choices for a design. Right? The goal is to understand the basic idea in which we did this. Since we have few minutes, maybe let's look at one more case. So let us say I have two transistors now. This is, let us say, a cascode. Let's take a cascode current source. So here it's a cascode current source. I know that I have to design for a particular current I0, and my goal is to maximize the output resistance. So here, what is the output resistance approximately? GM2 R02 times. My goal is to have a very large output resistance. I know the current, right? Let's see how we can design. And here, which of the two transistors is the actual current source? M1 or M2? This is the actual current source that is biased with a particular VGS and VDS. Okay. And this is essentially the cascode transistor, which is a current buffer. You push in current into the source, take it out from the drain. It's a current buffer. Okay. So, okay, let's see how we can solve for this. Let's see if we can do it quickly. So let's say start with M1. So what are the things I know for M1 now? Is there something I know about M1? Some parameter? The specs I have been given are what? I know the current and I know output resistance should be large. So at least I know that I know the drain current of M1 and I need to maximize this fellow. So what can you say about a parameter for M1 from this? I mean, this has to be larger. So what parameter of M1 is present here? RDS1, R01. So at least I know R01 must be large or GDS1 must be small. So which parameter I have information about now? Yeah, if you remember, this was another parameter. So I know something about GDS by ID, that it has to be small. Okay. Now my goal is to find the sizes, length and width. So what parameter I can look at now? Why? Because I know the current, I need to find the width. So one thing you can do is I can plot GDS by ID as a function of, let us say, ID by W for different lengths, say L1, L2, L3, etc. Okay. And then you choose a particular length for which you get a reasonably small GDS by ID. Fine. So that will make sure you choose the length. You fix some GDS by ID. That will tell you what is the ratio ID by W. So which means you know the current, you know this. From this you find the width. Okay. But again, remember you don't stop there, because you have to look at the operating point also. So let us say from this you find the operating point. Basically from the same plot, let us say you plot ID by W versus VGS. From this you find VGS. Okay. So let's say for example you find VGS to be 0.7 volts or something. Now this transistor must be in saturation. So I need to make sure the drain voltage is sufficiently large. And in this circuit, what is fixing the drain voltage here? Current through M2. How is it fixing that? sorry, yeah, if this is some VB2, my drain voltage is VB2 minus VGS2 at a current of I0. So I need to make sure this is sufficiently large. Okay, so which means we have to choose these two based on our VD requirement. So let us say I choose my drain voltage to be roughly I don't know, 0.6 volts maybe, will be in saturation. So which means I have to choose these two so that this is 0.6. Okay, so quickly let's do M2. So let's say now I have to design M2. For M2 I know the current ID. From the output resistance, what is the information on M2 I have? I know that my gain must be large, correct? This must be large. I need to find the width. So what do? I need to find these two fellows. So which parameter I look at now? I look at GM by GDS versus, no, I don't know anything about GM, right? I just know GM by GDS. I know the current. ID by W is a better parameter because I know the current. I can directly find width from ID by W. Again, you plot it for different lengths. Okay, L1, L2, L3, etc. You choose a particular length that will fix GM by GDS, ID by W. You find W. But again, you don't stop there. You have to verify that this is satisfied, right? So you find what is the VGS you have. So let us say you get the VGS to be say 1.2 volt for example. Okay, if VGS is 1.2 volt, what would be VB2 from this case? I mean, if VGS is 1.2 volt, what would be VB2? 1.8. Okay, my supply itself is 1.8. So which means, do you think this is a better choice? No, because I know this drain voltage cannot go more than supply. It will be much smaller than supply, so this might not be in saturation. So which means this choice is not great. So now you have to go and refine. So one thing you can do is, now I know that the problem is with VGS. So I can start with assuming a VGS for the transistor. Okay, so instead of doing this, I can assume VGS. So let us say VGS I assume to be 0.6 volts. So then I can go and plot VGS versus GM by GDS for different lengths. Okay, I know what is the VGS and I'll choose a particular length that gives me good GM by GDS. Okay, is the logic fine? And the moment I know GM by GDS, I can do the same thing back. I'll plot GM by GDS versus ID by W and find width from there. Okay, so design is not always just, you do it and get it done. Like I told you, once you design, you verify the transistors are in saturation. If not, you have to go and tweak. Okay, so I'll stop here. But I'm hoping that the basic idea seems okay.